Throughout your mathematic journey, at one time or another, I expect you've wondered what happens when x becomes infinitely large in a function. Now, you might be tempted to just blurt out the obvious answer, infinity, and, well, that's not exactly the worst answer, and in many cases, that is perfectly on point. For this polynomial, for example, if we try a million, a billion, a trillion, and we just keep going to infinity, well, we're going to see that the value increases, so we'd say that this does approach infinity. But oftentimes there are more complicated cases. Take this function over here, for example, 1 over x. Entirely unlike the first function here, as x increases in value, the total value is actually going to become less. It's going to decrease over time because take 1 over 10 or 1 over 100, as x becomes larger, the value is decreasing. This is an inverse relationship. So we'd actually say that this function is going to approach 0. So voila, that's it, right? If x is on top of a function, it's going to approach infinity, and if x is on bottom, it's going to approach 0, right? Well, unfortunately, as is a very, very common theme with calculus, nothing is ever quite that simple. As promised, here we have a bit more interesting of a function. So we have 3x plus 3 over x as x approaches infinity. And in this particular instance, we have x in the numerator and the denominator. So this clearly isn't quite as straightforward as the problems we faced up here. So what are we supposed to do here? How do we solve this? Well, let's start by dividing this function up and seeing if we can express it in different terms that makes it easier to digest. Now, looking at the separated form, we can notice that this 3 over x bears a striking resemblance to the 1 over x we solved earlier. And that's because this is ultimately going to yield the exact same result. This 3 is going to be negligible, and as x approaches infinity, this is all just going to simplify to 0, which means we can factor it out of our limit. And then that makes solving the rest of this much simpler. So we have 3x divided by x. Well, as x becomes infinitely large, these x's are just going to cancel each other out. I mean, no matter how large x is, a billion, for example, you're just going to wind up with 3 billion divided by a billion, which means you're left with 3. So that means that this entire limit is going to simplify to 3. And voila, there we go. That means that we've solved our very first horizontal asymptote. So let's go ahead and take a look at this graphically and see what this means. All right, so here we have our function 3x plus 3 over x graphed. And we already know that the limit of this function evaluates to 3. We've solved that. So now we can see that there's what we call a horizontal asymptote here, located at what appears to be y is equal to 3. And, well, considering what we found, that makes perfect sense. Now, what this horizontal asymptote represents is that this function is going to approach the value of 3 from both sides, as we can see. It's dramatically increasing in value from this side, for example, before eventually plateauing as it approaches the value 3. And that's because this function is going to become infinitely close to 3, but it will never precisely reach 3. Because remember, even though this limit is approaching 3, we're saying that this limit evaluates to 3, the limit is not equal to the exact value, and this function will never precisely equal 3. Because no matter how large x is, we're still going to have this extra 3 here that is disturbing the true equilibrium. Now, you may have noticed something interesting. We have a horizontal asymptote, as I've clearly outlined for us, but we actually also have a vertical asymptote here. And that's because we can see a very similar effect whenever x is equal to 0. So when x approaches 0, we can see that this function is going to approach negative infinity or positive infinity depending on what side we're at. Now, this limit doesn't actually exist since we're diverging to infinity from both sides and not even in the same direction. However, this still gives us a vertical asymptote because we're never touching x is equal to 0, because when x is equal to 0, we just get undefined behavior. That's division by 0, a classic, 3 over 0. And we're not able to really do anything with this. So we would say that this is undefined. Okay, well, that's great and fine and dandy and all that jazz, but how do we actually apply this information? Well, what we can do is whenever we have a limit as x approaches infinity, we can actually use that to evaluate a horizontal asymptote, assuming it doesn't approach infinity, because in that case, that would mean that the function is converging on a specific value. So there we go, that's a horizontal asymptote by definition. And then whenever we have this undefined behavior, this division by 0, well, that means that we can go ahead and say that there's a vertical asymptote there. So if we evaluate a function like we did over here and we get, for example, 5 over 0, then voila, that's going to be a vertical asymptote. And an important distinction to make here is that this is not equal to indeterminate form. Indeterminate form can result in many, many different types of behavior beyond vertical asymptotes. In fact, you're probably going to wind up with something that is not a vertical asymptote, so don't assume. Now, strictly speaking, these will both result in undefined. 5 over 0 is undefined, and 0 over 0 is undefined. But it's crucial to remember that the actual behavior of these undefined values is going to differ significantly. This indeterminate form means that more analysis is needed. 5, 0 means you have a vertical asymptote. So, there we go. Now let's move on and solve some problems. All right, so we have our first question here. Find the vertical and horizontal asymptotes of f of x if they exist. Then we have 5x squared plus 2x over 2x squared plus 8. Okay, this looks a little hairier than our previous problem, but it's actually not too difficult. So to find the vertical asymptote, all we need to find is where we get a situation similar to the one we covered earlier, where we have a number divided by 0. So we need to find out when this denominator is equal to 0. So we can go ahead and set that up down here. We have 2x squared plus 8 equal to 0. We subtract 8 from both sides, gives us 2x squared is equal to negative 8. We divide 2 from both sides, pretty simple. That gives us x squared is equal to negative 4. Now, without delving into the realm of imaginary numbers, this doesn't have any solutions. There is no possible number we can plug into x squared that gives us a negative number, which means this will never equal 0. So we can say that this will never equal 0. Definitively, it is impossible, which means that there are no vertical asymptotes. They do not exist. Alright, well, that was a little disappointing result. So this function doesn't have any vertical asymptotes, so let's try to solve for a horizontal asymptote. So let's just start off by remembering that the definition of a horizontal asymptote is the value of the function as x approaches infinity. So let's see here. We can see if it's consistent with our results. So looking at this graph visually, just observing it really quickly, we can see that there doesn't appear to be any vertical asymptote. We're not approaching negative infinity or positive infinity. We just seem to be staying around this interval from 0 to 2.5. And speaking of 2.5, in fact, that does appear to be our horizontal asymptote, because we can notice here this appears to be between 0 and 5, so 2.5. And this function, as x becomes infinitely large, and obviously we only have a small portion of infinitely large visible here, but just from what we can examine, it appears to be approaching 2.5 in both directions. So there we go. That means that we have our horizontal asymptote. We've solved this problem. Let's move on to the next. All right, excellent. So we have our next function here, x squared over x plus 1. Now, this one doesn't seem too difficult, so let's just get right into it and solve its vertical asymptote. So looking at this, we can go ahead and start by setting the denominator as being equal to 0 so we can find what x value might yield a vertical asymptote. So we have x plus 1, and well, this doesn't exactly take a genius to figure out. That just gives us x is equal to negative 1. And so now let's try to plug this value into our top here to see if we wind up with indeterminate form instead of a vertical asymptote. So trying that out, we get negative 1 squared over 0. So that just gives us 1 over 0. And yes, this is a vertical asymptote. So we can say that we do, in fact, have a vertical asymptote at negative 1. Beautiful. Now, what about a horizontal asymptote? All right, well, looking at this, we can see that this appears to be dominated by an x squared, and we don't have any x squared in the denominator here. So to make things a little easier to understand, let's go ahead and get rid of this one. And we can factor this one out because it's going to be completely superseded by these x terms. So in factoring the final value, it's going to be pretty much useless. No disrespect to my good friend 1 here. But that leaves us with x squared over x. And now using some simplification, we can go ahead and evaluate this as being equal to x. Wait, hold on here for a moment. If f of x is just equal to x as x approaches infinity, then that means that the function itself is also going to approach infinity, which means it's not approaching any specific value, it's just diverging to infinity, which means there is no horizontal asymptote. And we can observe exactly that. So we do have a vertical asymptote at x is equal to negative 1, but as x becomes infinitely large, the function just appears to diverge towards infinity and negative infinity, depending on the direction. So yeah, that means that our results were correct. All right, that's all from me for today. Thank you sincerely for watching. I very much appreciate it. And if you enjoyed or learned something, I'd also appreciate it if you liked, commented, or subscribed. But either way, have a wonderful day.